Hey there, my name is David Liu, and I'll be presenting on the fifth and final lab of Intro Physics 1 at Georgia Tech titled Choose Your Own Adventure. The purpose of this lab is to follow a basketball's trajectory using tracker and a computational model. This will incorporate the physical principles of Newton's second law and kinematics. I was inspired to choose this topic by the Puerto Rican NBA player and Georgia Tech alumni Jose Alvarado, known for his reaction, "Yes, I can shoot." I also felt that kinematics and projectile motion were the topics in the course that I struggled with, and so I wanted to target my weaknesses by connecting them to an activity that I was particularly passionate about. Shown here is a brief preview of the main results of the lab described in numerical form and vector notation. The position update formula and velocity update formula were essential in this experiment as they allowed us to predict what the position or velocity would be at a change in time later. These, along with the subsequent kinematic equations, were used in accordance with Newton's second law of motion. These were in the x and y directions and assumed constant gravitational force near the Earth's surface. For this experiment, I recorded myself shooting a basketball from beyond the arc at our campus rec center. The central unknown in this experiment was the initial velocity. There was no information on how fast it was shot. The time to the maximum height however, can be found from the kinematic formula. It is known that at the maximum height, the y component of velocity should be 0. Shown here is a video of the experiment when viewed through the tracker analysis tool and the graphs generated. The initial angle was found by tracker by angling the coordinate axes with the trajectory of the ball for the first 7 steps. Using a starter program provided by Dr. Alicea, I substituted each of the measurements of the initial conditions for each variable shown on the left, such as the location of the basket. Because it is assumed that this system operates in 2 dimensions, the z component of the position vectors and velocity vectors are all 0. The mass of the basketball was assumed to be approximately 0.624 kilograms. The model's predictions substitute values determined from previous slides, such as the initial position and velocity. The previous formulas and physical principles are essentially translated into code, which is also shown on the next slide. Shown here are the corresponding formulas on the right and the code on the left. The velocity update and position update formulas are derived from the momentum principle. And to find the initial velocity, which is arguably the most important value, as it determines whether or not the basketball reaches the hoop, the following formula was used and then rearranged to solve for v sub I. From tracker, delta t was found to be the duration of the video, or 1.433 seconds. Theta was 57.1 degrees. Y sub max could be then found from the height, initial velocity, and angle as well. Now this code block here is what allows the tracker position data to be imported as a CSV file and then read in GlowScript. Ultimately, the data are plotted in each iteration step on the 2 graphs, reflecting the x position over time and the y position over time. Each of those values are then printed when the CSV value is selected. So here is a video of what was depicted. It was assumed that if y ball equaled y basket, then the ball would go into the hoop. However, there were some unexpected findings, which led me to believe that there were extraneous variables inadvertently present in the experiment that affected its outcome. Now, here again are the main results of the lab described as they were depicted as printed outputs of the program. Notably, the basketball was portrayed as having been short of in the predicted or computational model, where in tracker it was visibly a make. So this led to me to consider potential sources of error. Though the conditions were idealized, a variety of errors may have been introduced. This includes not accounting for the rotational kinetic energy or backspin present in the system, which supposedly causes the ball to glide farther and higher through the air. Moreover, the drag force was also ignored. Failure to incorporate these variables into the kinematic calculations could at least partially explain the discrepancies observed between the computational model and the physical observations. Moreover, the z component could have been introduced as well. Now, addressing the what if of this lab's experiment, if drag and backspin were accounted for in this model, there would likely be a more accurate trajectory portrayed on the 2 graphs shown on the right, so that they would be nearly identical when overlaid on those generated by tracker, which are shown on the left. In short, this data has demonstrated that there may be slight differences between what is predicted and observed. This divergence can be accounted for differences between theoretical simplifications and real-world conditions. However, they can still be useful tools for predicting the motion of a system when some variables are unknown. Thanks for watching.